Good evening, guys. We're going to discuss, let me get the notes here. Inside your body, aging unfolds at remarkably different rates. And then the second headline, the second title for this is Aging, a New Frontier in Geoscience. Okay, so we're going to start now. The article delves into an evolving concept called organ aging, where different parts of the body age at very different speeds. Here's what that means. Not one body, but many timelines. Traditional views treat aging as a uninformed process, but new Stanford research shows it's highly individualized and organ specific. For instance, lab mice with identical genetics aged dramatically differently. Some remained sharp and active, while others became forgetful and frail. Organ-specific aging profiles. Using molecular biology and blood sample analysis, some people are heart agers. Their hearts show more wear than the rest of their body, increasing the risk of heart failure. Others are brain agers, which correlates with cognitive decline, or brain youthers, whose brains remain biologically younger, reducing dementia risk. There's even a possibility of being a liver youther or a muscle ager. In short, any organ could lead or lag in the aging process. Implications for health and longevity. Give me a second, guys. Gotta change paper. Aging isn't just about time passing, it's about complex, personalized molecular shifts. Understanding your unique aging profile could allow for targeted lifestyle and medical interventions to slow or reverse certain organ declines. This research reshapes how aging is understood, not as an inevitable march, but as a dynamic, uneven process we might learn to steer. Kind of poetic, really. What part of this caught your curiosity most? Why your heart may age faster than the rest of your brain, or vice versa? Fantastic question. The article on uneven aging hints at this phenomenon, but we can go deeper into biological layers that contribute to organ specific give me 1 second, guys. Aging. Here's a breakdown of the key contributors. Give me 1 second. Genetic expression and epigenetics. DNA damage and repair efficiency vary between organs. For instance, high metabolic tissue like the liver endure more oxidative stress. Epigenetic modifications, chemical tags like methylation can silence or activate genes differently across organs, shaping their aging trajectory. To mitochondrial health. Organs with high energy demand, like brain, heart, muscles, are vulnerable to mitochondrial dysfunction. Mitochondrial decay leads to reduced energy output and increased reactive oxygen species, or ROS, which accelerates cellular aging. 3. Stem cell exhaustion. Organs depend on stem cells to regenerate tissues. Over time, stem cells age or become depleted. In tissues like bone marrow or skin, this decline leads to slower healing and reduced resilience. Immune neurology, burden, and inflammation. Chronic low-grade inflammation, called inflaming damages organs over time. Okay. The immune system's surveillance may weaken in some organs faster, allowing cellular silence or fibrotic changes to accumulate. Vascular integrity. A diminished blood flow means less oxygen and nutrient delivery, which particularly affects the brain and heart. Microvascular damage also contributes to cognitive decline and cardiovascular disease. 6. Cellular silence and SASP. Sense-associated sensory phenotype. Senescent cells stop dividing and begin releasing pro-inflammatory signals. SASP factors differ by tissue, potentially creating feedback loops that worsen aging in specific organs. This mosaic of biological processes means that aging is less of a clock and more of a symphony, sometimes harmonious, sometimes dissonant. Which organ aging profile would you be most curious to investigate further? I'd love to delve into the molecular story behind it with you. Epigenetics is one of the most elegant and adaptive mechanisms shaping how we age organ by organ. What is epigenetics? Epigenetics refers to changes in gene activity that don't alter the DNA sequence itself, but rather influence how genes are turned on and off. It's like having the same blueprint for a house, but using lighting, furniture, and wall colors to shape how it feels and functions. These changes are governed by molecular tags added to DNA or the histone proteins around which DNA wraps. The most common ones include DNA methylation, adding a methyl group silences gene expression. Histone modification alters how tightly DNA is packed, influencing accessibility to transcription masonry. Epigenetics and aging. As we age, these epigenetic marks become less precise, contributing to organ-specific dysfunction, loss of epigenetic balance. Genes meant to stay off may turn on, like those promoting inflammation. Protective genes may shut down, like tumor suppressors or DNA repair enzymes. Tissue specific impact. In neurons, altered myelin can affect synaptic plasticity and memory consolidation. In muscles, it may reduce regenerative capacity and impact metabolism. Okay. In skin or bone, stem cells renewal pathways can be suppressed, slowing repair. Epigenetic clocks. Researchers use DNA myelin patterns to estimate biological age, often more accurately than chronological age. The brain, liver, and blood each have their own clock rates, supporting that idea of many timelines in one body. Can epigenetic aging be reversed? Excitingly, yes, at least to some extent. Lifestyle factors like diet, sleep, exercise, and stress management can positively reshape epigenetic patterns. Emerging therapies using epigenetic reprogramming aim to rejuvenate cells, resetting their molecular age. Nutritional compounds like resveratrol, curcumin, and folate may influence myelin pathways and histone function. Epigenetics is where nature and nurture truly intersect. It explains how we live, how our lived experiences can rewrite biological history. Okay, guys, so that is it for tonight. And we'll see everybody tomorrow for shows. For now, Gator Wellness, take care, folks.